So for those that don't know me, I'm Steve Whitaker. I'm part of the team in applied research that looks after our global research relationships, and in particular, I look after our relationships with US universities and business schools, including our 30-year relationship with MIT. Just before I hand over to Armando, who's our guest speaker today, I just want to just frame the talk a little bit. So for about the last 70 years, as the digital revolution's unfolded, pretty much everything in the digital revolution has been built by kind of human design and human coding. But over the last 5 years or so, we've seen machine learning moving from just being something we use primarily for analytics and understanding to something we're beginning to use for kind of building and creativity and engineering. And we've seen some pretty amazing things being built. So, synthetic pilots that can beat human jet pilots in dogfights. We've seen world-class game players. We've seen systems that can paint as well as the world's greatest artists. None of these things would have been possible with traditional programming. And as a result of that, what we're beginning to see is a shift in the way that we think about making things. And part of that is this shift between things like learning and programming, between data and specifications, between code and models. And obviously the impacts are going to be quite profound because they change the whole way we think about things like software engineering. And that's it's a huge enterprise kind of globally. So clearly, this is again one of these things that's going to have multiple dimensions to it. I'm going to have to look at this in like a number of different ways, kind of pick up the idea and turn it around and poke it from different directions, which I think is why today's talk is particularly relevant, particularly timely. So it's my really great pleasure to introduce Armando Sol. Armando leads the computer-assisted programming group at MIT CSAIL. He's also the associate director and COO. So Armando will speak probably for about 40 minutes, and then we'll do Q&A. If you have any questions during the talk, please add them into the chat window, and we'll try and address them either as we go along or at the end. Try as many as we can. Sarah's asked me to mention that the talk's been recorded. So with that, I'll hand over to Armando. So good morning, Armando.
Hi, good morning. Thank you. Thanks for the introduction. And yeah, so this is something that I've been doing a lot of thinking about. And if you look at traditional machine learning versus traditional coding, the way most systems we have in place today have actually been built, they might as well be operating in different planets. They're very different approaches and very different paradigms for getting functionality. So, for example, when you're talking about coding, generally you're talking about something that is very precise, right? One of the hallmarks of computer programming is that it gives you this immense precision to tell the machine exactly what you want to happen. But that also makes it rigid. Code is very modular. You can build it in pieces. You can understand each one of these pieces independently. You can zoom in or zoom out to different levels of abstraction in the code and understand different components and what they're going to do in terms of very clean, clear interfaces. It is a very manual, time-consuming process. There's traditionally been very little help in actually putting the code together. There's a little automation that modern programming languages bring to the table, things like garbage collection, but in general, we're talking about a very manual process. But it is very scalable. We can build really large systems using traditional programming methodologies. And along with this manual aspect comes the notion that the programmer knows best, and the programmer has to be in full control of what's happening. By contrast, machine learning has traditionally focused on more approximate behaviors, and that can give it a lot of flexibility, a lot of robustness. But especially when we're talking about deep learning and when we're talking about training end-to-end behaviors, usually what you end up with is a very large model that performs a task. And what is happening inside, who knows? And how is the task being broken down? Who knows? What we get to see is a large model that is performing a complicated task in ways that are difficult for humans to understand. But it is completely automated. You're able to provide data, or in the case of reinforcement learning, some training environment, and the system gets to figure out how to solve the problem on its own. And modern deep learning techniques are themselves very scalable. You can get very complex, you can train very complex functionality, and functionality that potentially could have taken many, many lines of code. And you can get a neural network to perform this functionality. And the philosophy is quite different. It's not programmer knows best, it's let the data speak for itself. The less we bake into the model, the more the model has flexibility to do whatever the data tells it is best. Tends to be better here. And so one of the questions we've had for a long time is, what if you need some of both? What if you need some of the advantages of machine learning, but in a context where you really need precision, or where you really need modularity, or where the programmer really does know best, and you really do want the programmers to be in control of what's happening? And so one technology that we have been exploring for several years now is program synthesis. And the high-level goal of program synthesis is to bring some of these automation that you get in machine learning and bring it to programming. However, without losing some of the things that make programming very powerful. So in particular, there's a class of techniques that we've been working for many years now, called syntax-guided synthesis, where the idea is that you can bring together behavior constraints, some information about how the code is supposed to behave. And this can be in the form of input-output examples, so not that different from, say, the kind of data that you might provide to a machine learning algorithm, except possibly for the scale. Sometimes when you're talking about program synthesis, you want to be able to generate a piece of code from relatively small numbers of examples. But you can also provide other forms of behavior constraints, for example, safety properties, constraints that you absolutely need to be satisfied by the code. This is something that traditional machine learning is not so good at these hard constraints that absolutely have to be satisfied by the code. But in addition to that, and the thing that really makes this very powerful, is that you can also provide information about how the code should look like. So these are structural constraints on the code that you want. And this might take the form, for example, of program components. These information about exactly what are the building blocks that need to be used to build these programs. So it cannot just be some blob of neurons. It has to be a program built from a certain set of components. Or even it might be a skeleton of the code that you want to receive, or even a distribution, a prior over the program structures that tell you programs that look like this are more likely than programs that look like that. And the idea of program synthesis is to combine together both of these kinds of information about the code you want to give you an actual piece of code, one that you can execute, but in some cases you might also want to inspect. And one where, because of this control that you have over the components that make it up, or over the structure, you get a lot more predictability in its behavior. So over the years, there have been quite a few success stories around this. For example, data structure manipulations, the kind of data structure manipulations that people learn how to do in their early programming courses. They can actually be fairly automated using these kind of techniques, and you can even synthesize verified implementations of some of these data structures, even concurrent data structures in some cases. Data wrangling and text manipulation, that is a domain that has actually seen a lot of interest from this community. If you use Excel nowadays, for example, the flash fill functionality that is part of Excel that allows you to take some columns of text and then extract some information from the text just by providing some examples of the information you want to extract. and then generalizing from that. That is technology that came from our community. In fact, a former student of our group was actually pretty deeply involved in bringing this functionality about. And there's many other domains, there's many other success stories. For example, the kind of bit level manipulations that you see in things like network protocols is something that we can actually automate very, very aggressively. And there's many other things. So these gives us, on the one hand, the precision and the modularity and the programmer knows best ethos of code together with some automation. But it's still not solving the full problem of bringing these two things together. First, the automation, we could say it's automated-ish. We can automate at a small, at a very local level, but there's still a fair amount of expertise that is required in terms of using these tools and in terms of setting them up and in terms of really guiding the tool towards the right answer. And scalability can really be an issue, right? In particular, we can synthesize fairly small pieces of code. And when I say small, I really mean small, on the order of maybe 10 lines of code. Now, if you have the right language and if you have the right abstractions, you can build some pretty powerful things in the scale of 10 lines of code. But that's still a pretty significant limitation. And partly it's because these techniques are trying to solve these problems, essentially from first principles, from really understanding what each of these components and each of these building blocks do, and then being able to explore very efficiently how you can combine this in order to get the functionality that you want, right? And as much as we try to support different forms of interaction with the system, there's still a significant bottleneck in terms of how do you tell the system what is it that you actually want it to do. And so in recent years, we've actually been exploring ways of more tightly combining program synthesis and the kind of techniques that we have studying that are looking at these problems very symbolically and are looking at them from the perspective of generating code, generating something that a programmer would recognize as a program, and combining them with neural techniques in a way that allows you to really leverage the best of both approaches. And so we have been exploring just different setups and different combinations of these two techniques to address some of the shortcomings of these existing approaches. So at this point, we have actually explored a few different paradigms of bringing these two kinds of techniques together. And so, for example, one of these paradigms is what we call neural guided search, where essentially at the end of the process, what you want to get is just a program, something that is recognizable as a piece of code that maybe a human could have written, but where you can leverage the neural network, the power of the neural network, to guide this code search towards the code that you actually want. And so this can have many benefits. On the one hand, it can deal with the automated-ish aspect of prior program synthesis techniques, because now the neural network is able to take goals at a potentially higher level of abstraction. It's also able to guide the search better so that you need less human effort in terms of generating setting up the problem and generating the code. A different paradigm is one where these components act in more of a pipeline, where you take advantage of the ability of the neural network to take very unstructured kinds of inputs, right? Things like images, pictures, natural language, and translate them to a form that is more suitable for symbolic reasoning, that is more in the world of symbols and constraints that this more traditional program synthesis techniques can understand. And in this way, bridge this gap between the level of abstraction at which programmers want to talk about their functionality and the level of abstraction that is necessary for these tools to operate. Another paradigm that we're really excited about and interested in is more of a program extraction paradigm, where we start by saying we have this remarkable ability in deep learning to construct these deep neural networks that can learn things that would be difficult even to specify what it is that we want, especially in the reinforcement learning setting, where you have some goal, maybe you have some simulation environment, and the deep reinforcement learning algorithm is just able to figure out how to do it, how to solve the problem. But then, once we have that, what we want to do is extract from that a program, a clear, clean piece of code that emulates the behavior of that deep neural network. And now that we have the neural network that has figured out how to solve the task, it can teach the synthesizer how to solve it in order to help us get a cleaner, more interpretable piece of code. Now, the end goal is to really be able to get to the point where we can have full, complete, arbitrary combinations of learned components and of program-like components, where the system could automatically figure out what are the parts of the job that are really better left just to a neural network, where they don't have a lot of structure, where you really want the data to speak for itself, and what are the parts of the problem that are better done with more traditional looking code, where you want to leverage the interpretability or the predictability of particular program structures or particular components that you might have that already exist. And how do you, and could you actually get a system to automatically figure out what is best done by what? That is really the holy grail of this space. We don't yet know how to do that, but I want to give you some examples of the first three to give you a sense of how these things might come together. And one of the things that I should say too about this space is that when you start looking at things from this perspective, you can start solving problems that are not obviously software engineering problems, but they're also not obviously problems that you could solve with traditional machine learning. For example, one domain that we have been particularly interested in is computer-aided design. And one of the things that you have today in modern CAD systems for just physical objects is that even though people interact with them mostly through a graphical user interface, internally, the internal representations look a lot like programs. And so I'm going to use that as an example, or a simplified version of that as an example, to talk about this setting of neural guided search. And one way to think about this neural guided search, it's a little bit like what you're trying to do when you're trying to do machine translation. When just like you might want to go from, say, French to English, in this case, you might want to go from a goal or a specification to a program, a piece of code. But as you might imagine, this is actually quite different from translating from French to English, because code has a lot of things that make it special. On the one hand, it's brittle, but on the other hand, we can run it. We can actually see what happens when you run a particular piece of code. And this is something that we really leverage in some of these techniques. So for example, in this particular paper that I'm going to talk about, the idea was that you have some goal and you have some initial state for your program. And so what you want to do is I want to learn to synthesize incrementally, rather than something where you just tell it, here's the goal, and it turns on it, and it gives you back what it expects to be the perfect working piece of code. The idea is that you want to produce this code incrementally, one instruction at a time. And when we talk about instruction here, we're not talking about, let's say, assembly code. We're talking about a component that you might have a priori decided that these are the components that are going to make up your language and that you're going to be building code from. And so the idea is, from the goal in this initial state, you produce the first instruction in your language. But from that first instruction, what you can do is take advantage again of the fact that code can actually be executed. You can run this instruction, see what happens. And then from that, you can actually feed this new state after this instruction has executed, combine it with the goal, and the neural network can now spit the next instruction, which can then be interpreted to produce a new state that you feed to the network. Notice that the network, in this case, doesn't even get to see what the code looks like, because after all, it doesn't care what the code looks like. What it cares is what that code is actually doing, because what the code is doing is really tells you exactly what's going on, versus if you get to see the code, then you have to be able to deal with the fact that the same behavior could be produced by many, many different combinations of instructions. Code has this property that you can often say the same thing in many different ways. And so what this allows you to do is to build the program incrementally. Now, oftentimes, the network is not actually going to be able to tell you exactly what the next instruction is going to be. But for example, if we think about this goal, where this domain of computer-aided design, where the goal is you have some part and you're trying to figure out the set of operations, the set of geometric operations that are going to give you that part. Well, so you start with an empty part. There is no part, right? So the first instruction might say, well, you need to build a rectangle, or in 3D, you might need to build, create a box with a particular set of dimensions, right? And then that's the new state. So the next instruction might say, okay, now you have to produce a circle, or in 3D, a sphere with a particular set of coordinates and dimensions, right? And that's the new state. Now you have these two shapes. The next instruction might say, okay, now you have to subtract one from the other. And that's how you see this. And so at every step, the network is trying to figure out what the next instruction should be in order to get closer and closer to the goal. Now, in general, it's not actually going to tell you this is exactly the next instruction that you should produce. Instead, what it's going to give you is a distribution of possible instructions. It says, maybe you need to subtract the shape in canvas number 3 from the shape in canvas number 1. But maybe you have to subtract the shape in canvas number 2 from the shape in canvas number 3. Or maybe you have to draw a new rectangle, right? And so from these distribution, it has to choose what the next instruction should be. And so in doing this, at every step, it actually has a whole tree of choices that it can make. And what we find is that if you actually train a neural network, not just to give you these proposals, essentially this policy that is trying to give you these proposals, if you also train a value network that looks at these proposals and decides which one of these looks more likely to be the right thing to do in the context of everything that's going on, which one of these states looks like it's on the right track to make it to the goal. What you can do is you can actually do a search over all of these possibilities, taking advantage of the fact that when you have a program that behaves as you want, you can tell that the program is behaving as you want. You can test the program, you can run the program, you can even run some of the program analysis tools that we've developed over the past few decades to automatically discover bugs in this program and figure out that some of these programs are not actually doing the right thing at this point. And so in this way, you are able to find programs that actually do the things you want. And you can do this not just in this domain of 2D drawings, you can do this in this domain of 3D shapes. You can do it in domains, for example, dealing with text manipulation. This is a pretty important domain for things like data wrangling, where you want to provide examples that say, I want text like this to be transformed into text like this, or I want text like this to be transformed into text like this. And the system is actually able to come up with a program that generalizes from those examples and is able to generate these transformations for other domains. And this kind of system can do it much better than prior systems. So that's one example that of an instance where you want to leverage the neural network to help you hone in on the code that does exactly what you want. And you want to be able to leverage the fact that oftentimes you're trying to solve many related problems. You have just a task, a programming task that you have to do over and over again. Data wrangling is a good example. It's an integral part of most data science pipelines, just be able to extract the right data from text files, for example, and being able to teach the machine how to do that with a few examples is really powerful. Now, for different kind of combination, we can look at this pipeline approach. So here, the idea is we have a goal expressed in very amorphous, unstructured terms, and you want to translate it into a very crisp, clear goal that now you can leverage these more symbolic techniques to get a program that satisfies that goal. And so one example of that is from this different paper, where the idea was that we want to be able to take hand-drawn diagrams. These are the kind of diagrams that you might use in a paper or in a presentation. And what you want to do is take this hand-drawn diagram and generate a piece of code that produces that diagram. So the idea is that not only can you now generate a very clean version of the diagram, but if it's expressed as code, it means that you can now generalize from the diagram, so that, for example, if you drew this 3x3 grid, and then later you realize, oh no, actually, I really needed a 4x4 grid, you just change a parameter in the program and you get the new grid, right? This is one of the advantages of code. In that modularity also comes a lot of flexibility, because code can have very clean interfaces. You don't just get a model that produces this image, but you get a model with a knob that you can tweak in order to get different versions of this image, right? And so what do we want is we want to go from this hand-drawn figure to a piece of code with loops, with conditionals, but we're not going to do it in one shot the way we might have in this neural guided search paradigm. Instead, what we're going to do is we're going to follow this two-step process, where first we're going to train a neural network to simply understand what's happening in this image, to identify all the elements in this diagram, identify all the circles and all the lines, and then that now becomes the new goal, the specification for the symbolic program synthesis process to go and figure out what should the code look like that is going to produce those elements that were identified by the neural network. And so what you get from that is you get this ability to generalize from these hand drawings. Now you can see that the generalizations are not always perfect. And part of the reason is that the generalizations are driven by the language that you have in order to describe these things. So for example, if we look at this picture right here, right, when it tries to generalize it, what you can see is that it's basically generalizing based on the coordinates of the starting point from of these lines. And the reason for that is that in the language that we've given it, there is actually no notion of a line being attached to a circle. Instead, it's done based on coordinates. There's some starting coordinate for this line and some starting coordinate of this line. And so when it tries to generalize, based on the coordinates of the lines. If instead the language actually supported the notion of an arrow connecting two circles, then it would actually be able to generalize. And this is actually one of the both advantages and disadvantages of this kind of very symbolic approach. We're moving from let the data speak for itself to the programmer knows best. And in this case, the programmer is whoever described the original abstractions that could be used to generate these diagrams, the original language that can generate these diagrams. And so in this case, because the language, it does not have this concept, then the system does not just discover that concept on its own. But you can see that it's able to do some pretty meaningful generalizations. Another thing that it's able to do is that by reasoning at the level of code, at this more symbolic level, you're able to make up for errors in the original interpretation that the neural network gave. So for example, from this image, the neural network hallucinated that, well, this kind of looks like an arrow. Maybe it is an arrow, right? And so if you look at all the elements that the neural network identified, one of those is actually an arrow. But then when you go to the more symbolic reasoning, and you're actually trying to generate a program, the synthesizer can tell that, yes, there is a program that can generate this, but there's a much simpler program, that much cleaner program where everything is the same. And so by allowing it to trade off the precision with which it matches the output produced by the neural network against a prior over the space of programs that tells it that simpler programs are significantly more likely than more complicated programs, it's able to actually correct for this error, right? And so the other paradigm that I want to talk about briefly is this program extraction paradigm. And at first, it might seem a little bit counterintuitive. You already got this neural network to do what you want. Why then go to the trouble of building a program that kind of imitates that behavior, maybe not even as well as the neural network itself? And the reason is that you might have other goals that are more difficult to enforce in the neural network, but that can potentially be enforced by construction in the underlying program that you're generating. So for example, in this project that was actually a collaboration with Martin Reinhardt, also at CSEL, as well as two different faculty members at Penn. And this was a project by student Jivana in Ala. So in this project, the idea was to look at the problem of coordination among drones, essentially, autonomous agents that are trying to move from one place to the other without crashing into each other. And one of the things that they sometimes have to do is communicate with other objects to coordinate to make sure that they're not going to crash into each other, right? And so for many of these behaviors, whether it is just to make sure that all the drones in the same team don't crash with each other, or to make sure that drones in different teams don't crash with each other, they might need to communicate. And so people have looked at this from the perspective of deep learning, and in particular, there's prior work that has shown that you can actually have a transformer-based architecture that works really well to have each agent on the one hand figure out what messages it needs to be sending, but also each drone figuring out what other agents it needs to be paying attention to, what other agents it needs to communicate with, so that these messages are combined and then are given to a policy that decides what to do next, right? And this works pretty well, except one of your goals is not just to make sure that drones don't crash, but also to minimize the amount of communication that you have between these agents, right? So you want to minimize the maximum amount of messages that every one of these drones has to send or receive. And this is where the transformer network doesn't do so well. It is requiring fairly significant amount of communication between all of these different drones. And it's hard to tell a priori how much communication you're actually going to get until you've run the thing. By contrast, in our approach, by extracting a program from this transformer, we are actually able to get significantly less communication. And in this case, each one of these clusters corresponds to one of those teams that we're talking about. So you can see that there are significant communication among the team and also communication between and different teams that have to cross each other. And so the idea is that we're replacing the original policy with a program that is trying to now be built by construction to make sure that you don't have a lot of communication. So for example, the sort of things that this program can do is define a region and then only focus on the agents within that region, and then within those agents, pick one at random to communicate with. Another thing that these programs might do is that they might pick a region, and then within that region define a function, and then only communicate with the agent that maximizes that function. And so by construction, this ensures that you're only communicating with one of these agents. Now, you can have multiple of these rules, and this allows you to communicate with multiple agents together. But the point is that now you can actually have very tight control over the communication. And so compared to the transformers, and even compared to other kinds of baselines, we can see that in terms of performance, this approach can actually do quite well. It can do almost as well as the transformers from which it was trained, but with significantly less communication in many cases, because you have these much tighter control at the program level of what can happen, right? And you can actually take some of these ideas further. So not just focus on one of those paradigms, but potentially mix and match and allow the system to really combine symbolic and neural mechanisms in really interesting and intricate ways. For example, one of the things that we talked about before is, again, one of the big advantages in deep learning is you can let the data speak for itself. You don't have to trust the programmer. And we saw this in the case of the hand drawings, where because we were tied to the abstractions created by the programmer, the system did not have the flexibility to identify certain patterns that were actually pretty important for some of those generalizations. And so one of the questions we had was actually, could you let the system not just figure out, hey, here's a bunch of components and now figure out how to connect them together, but could the system actually figure out what these components ought to be in the first place and figure that out from the data to let the data speak for itself? And so in order to illustrate how we can do this, here's a domain where we want to, that I like because it's very visual. And what we want to do is we want to be able to generate programs, little programs that produce intricate shapes like this. And so what we have is we have an algorithm that what it does is first, it runs essentially neural guided synthesis on all the problems that you give it in the corpus. And it starts with a fairly low-level language. So in this domain, the low-level language basically is just saying pen up, pen down, make a few, move in a particular direction. It can do arithmetic too. And so for most of these problems, they're too complicated to be able to generate a program that operates that way. But for some of them, it can actually generate the program. For example, this one is just a line. Of course, it can generate a program to just draw a line. But the idea is that now you can take these programs, and you can think of these as sort of analogous to when you're awake in the world. And this is an idea that has a long history in AI, these wake-sleep algorithms. And so the idea is, first you're awake in the world, you're doing things, you're acting on the world, you're solving problems. But then at some point, you go to sleep and you consolidate all of those memories, all of those things that you learn how to do during the waking phase. You're consolidating them into more compact representation. And this is where you're trying to analyze these programs and derive from those programs a language that you can actually use to describe these programs more concisely. And not only that, you can also train this neural network in order to get better at discovering these programs, so that when you go back to the waking phase, you can actually do a better job. Now that you have these better language, now that you have these better neural model to search for programs, you can find solutions to more problems. And those solutions to more problems, now you can close the circle. You can go back and then from those discover better components that will help you do what you want. And so in this case, for example, the system can learn components not just to draw things like circles and arcs and spirals, but it can also learn even higher level concepts. It can learn, for example, a routine that takes as an input parameter the just another drawing routine, and then create a radially symmetric drawing by just repeating the other drawing over and over again in a radially symmetric pattern. And so, but the system is able to build in these hierarchies of abstractions. First, low-level components to do simple things, then higher-level components that build on those lower-level components, and then higher-level components still that build on those lower-level components, so that after a few iterations, it's able to generate fairly intricate shapes, while still not having to generate massive programs, because it's already built up the abstractions that are needed in order to build these bigger programs. And so ultimately, the idea is to get to the point where we get many of these benefits of coding. We get the precision, we get the modularity, we get the scalability, we get the ability of the programmer to really put their knowledge down when they know best. But also you get the flexibility of neural networks when it's necessary, the flexibility to deal with less structured inputs. You also get the automation. You also get the ability for data to speak for itself, to not have to bake in all the knowledge into the system to begin with. And so this is what we're aiming for. There's still a long way to go. There's still a lot of research to be done, but we think that there really is a big opportunity in this space to get not just the tools for machine learning and AI to help us build better programs, but also we leverage the benefit of a lot of these technologies that we have built around programming and around code and help them build better machine learning systems. Really not think of these as two separate realms, but think of them in a more integrated way. And so with that, I think that's about 45 minutes or so.
Amanda, that's absolutely fantastic. So before we open up to one of the questions, I just wanted to use like host privilege just to ask a couple. So one was, I know you've been doing, the college been doing some work about learning across kind of more traditional programming languages and abstractions. I wonder if you want to comment on some of the types of traditional programming structures like recursion that you've been able to extract. And then the other one was, I know you've been doing some really interesting work about extracting programs from complex physical systems like physics, like biology, and then potentially which could be applied to things like process mining in complicated systems and those sorts of things. So I don't know if you want to touch on those two areas at all.
Sure. So let me talk about the second one first. So we actually have a new project that is it just kicked off last year. It's funded by NSF, and it's a large interdisciplinary project where we're looking at applying these techniques to understand nature and to understand the physical world. And I want to share just very briefly a slide here where of the kind of domains that we are thinking about as part of that project. So the domains that we're really, really interested in that space, one of them is organic chemistry. The other one is RNA splicing, and the other two are cognitive science and computer systems, right? And the idea in all of these is that we want to learn models that don't just say, oh, here's what's going to happen, right? In the case of a computer system, for example, we want a model that doesn't just tell you, oh, yes, this is how your program is going to perform when you run it in this kind of system, but we want to understand what's going on internally. And this domain of RNA splicing is particularly interesting in that realm. So RNA splicing is about how when proteins are created, what you have is you have DNA that gets transcribed to RNA. And traditionally, we think of it as this RNA goes out to some ribosome that then produces a protein. But in reality, what happens is that this RNA, before it goes out to be transcribed into a protein, actually gets processed and it gets spliced into pieces, it gets reassembled, and then you generate a protein out of that. And so out of this splicing process, what you have is you have different chunks of these RNA that just get cut out. And what we'd like is a model that is able to tell you exactly where these pieces that are going to get cut out start and end. And we're in a very peculiar situation. Biology is in a very peculiar situation where on the one hand, you can take everything that we know about this process, about the biochemistry of this process and how it works, and use that to make a prediction. And you can end up with highly interpretable models that capture a lot of domain knowledge, but they're not very high fidelity. We can explain something on the order of 60% of what can be observed using these models. Or you can train a deep neural network that gives very high fidelity, above 90% in terms of making these predictions. But it's a complete black box, and as such, it's kind of a dead end. You cannot really use it to understand what's going on or to make to help you design therapeutics, for example. It's much harder because it's not connected to everything we know about the biochemistry of this process. And so the goal is, by doing this combination of neural and program-like models, to be able to get a model that approaches the performance of these deep learned models, but that at the same time has these connections to the biochemistry, to what we know about these processes that then allow us to really leverage these models to improve our understanding of these biochemical processes. And so that's just one example here of what we are looking to do in this space.
But can you say a little bit about the programming language example as well? That'd be, I think, really interesting to people.
Sure. So in the case of programming languages, so I've talked a little bit about some of these data wrangling examples where generally you have text data. So for example, a really common scenario is you have some log files from a system, right? And a big tedious part of dealing with data from the real world is you might have some log file that comes out of a system, and you have to write a piece of code that usually in Python or something like this, that goes and parses this text file and extracts from it the relevant information that you actually need in order to make decisions about this computer system. And these are often just intricate string manipulations that you're doing in order to do this. And that's the kind of program that these days can be automated fairly accurately. We've also done work at a much higher level of abstraction where you're dealing, for example, with how to use complicated object-oriented APIs. In fact, there's some really compelling work in this space, not from our group, but from a different group in the community led by Swarat Chowdhury, where they've trained, they've used the neural guided synthesis approach that I described earlier to allow you to give some hints about the Java code that you want that uses some particular API. So let's say, for example, you're working on Android and you're trying to figure out how to initiate a Bluetooth connection. So you can give some hints about the fact that you're talking about Bluetooth, the fact that you're trying to open a connection, and then it helps you synthesize the actual code that is going to go and initiate the Bluetooth connection. For example, trained on large amounts of code in GitHub.
Fantastic, thank you. So I think we have some questions. So, so Gilbert, I know you got your hand up. Do you know chip in?
Yeah. So thanks a lot. Wanted to ask how you express the goal. I mean, your CAD example. I mean, where I'm coming from is how do you express goals for enterprise-wide systems? Okay, because so if you take, let's say, a transportation system, there could be an appointing slot, there is a billing, and so on and so forth. Do you see this approach being able to handle that? That's my first question. And then the second one is programming as it stands today requires a lot of tacit knowledge of the programmer. How are you able to handle that?
So both of those are really good questions. So these we call these the intention problem, right? How do you actually get all the information about what the programmer is trying to do? We have pretty good answers when it comes to doing these at the low level. So for example, for this project that I just mentioned, where they're trying to show you how to use these potentially complicated object-oriented APIs, the specification comes in the form of essentially keywords, right? And sequences of keywords where you say, I want to, I'm dealing with Bluetooth and I want to open it. And you might even know some of the types that are going to be involved, right? So maybe you know, for example, that that you're going to need, you're looking for the thing that uses the stream buffer and that involves the open file function, for example. And so from these keywords, you're essentially leveraging these to do sort of keyword search over code. And that can work pretty well at the level of small scale piece of code where you're using this kind of technology to assist you in doing things. In a project a while back, we looked at the problem of graphical user interfaces. And graphical user interfaces, one of the things that they have is that often you build them from frameworks that other people have used before. And so there's a lot of these programming by imitation, if you will, where let's say you want to go to a web page and you see that they built some functionality using some framework, and you want to be able to just point to it and say that thing that web page just did, that's what I want to learn how to do in my web page, right? And so now that gives you a very rich source of information because you can actually probe that existing code and look at what that code is doing and look at what was it that the programmer had to do at the level of user code that then led the framework to do what it was doing, to do what you observed in the screen. And so again, you're still talking about something at a fairly local level, how to implement a particular feature in a particular piece of code. I think the question becomes much harder when you're talking about a larger scale and when you're talking about something that you wanted to help you at the level of software design, for example. Now, I don't remember what was the other part of the question.
It was how related, how you express your goals for the CAD example.
Oh, so the CAD example was actually quite interesting because the problem that we were focusing on is, given an actual physical part, could you rediscover the sequence of geometric operations that could be used to reconstruct that part? And so this can be useful, for example, for legacy things, right? If you actually have just a chunk of metal lying in a workshop, an actual machine part for which that comes from the pre-CAD age, right? And you're trying to build a CAD model for it. You'd like to just be able to put it in a scanner, get a point cloud out of it, and from that point cloud, generate the set of geometric operations that produce that part.
Right. Thank you very much.
Thanks, Gilbert. So we had an interesting question from Rowan, which is one about I guess about where this is going and the scale of it, and at what point programmers' jobs disappear. And the thing that strikes me is that you'd mentioned I guess all the revolutions in image processing happened when we suddenly had things like ImageNet and stuff, and then you're talking about processing code bases the size of GitHub, and the availability of cloud scale computing to do these searches. So where do you see the future of this going in terms of kind of how this could grow and become as important as things like deep programming of video and images and those sorts of things, and with the programmers?
So that's a really good question, and whenever I get the question about when is this going to displace programmers, I like to remind people that back when Fortran came out, right, the first programming language, it was sold as the Fortran automated programming system, right? Now that we had Fortran, programming was going to be a thing of the past, right? Now people were not going to have to program anymore. They were just going to write Fortran, and then the machine would do all the programming for them without bugs. And now we read that and it seems laughable, right? Why? Because what happens is that now that's what we call programming, right? Writing in a high-level language. That's what we call programming, right? And figuring out the errors in those programs in high-level programming languages. That's debugging, right? The bugs that people were thinking about when they were and the kind of programming that people were thinking about when Fortran came about, involving what register did I put this, and exactly what address in memory does this go, and what address in memory does this go, right? Nobody thinks in those terms anymore. At least most programmers don't. But what happened instead was that all of a sudden we got to this cool new technology in the form of compilers and programming languages, and now we became way more productive in how we can write code. And that meant not that we now needed fewer programmers, it meant that we now needed more of them, because now the kind of things that a programmer could do were so much more sophisticated and so much richer that all of a sudden programmers became way more valuable. All right, and I think there's no reason for things to be different with this kind of techniques, in the sense that at the end of the day, you still need somebody to design the systems and to tell you what the system ought to look like and what the system is supposed to do. And if now you can go from that to code much more efficiently, it means that the people who really know, the people who know how to go from high-level fuzzy understanding of the domain to a software architecture and to a program solution will be even more valuable than they are today, and we'll be able to do way more with software than we can do today.
I think that's a very astute answer. I think if I were to like hover 20,000 feet above sea sail, the thing that strikes me is that every architectural and programming and system decision that you have to make in building a system, now learning becomes a valid architectural choice for those elements. And I think this is the whole thing about how do we encapsulate learning into every part of the design and kind of implementation process. And I think that's the kind of a set of mental gymnastics that we're going to have to go through. And this kind of program synthesis is very much part of that, where you say, well, some bits of code I'm not going to write themselves. I'm going to show it some examples of what other people have done. Other places you can say, no, I need this code. And I think that as we begin to think about large software-driven enterprises, getting good at that, understanding the modularity of the problem and which bits of learning can support better than programming, how they play together, I think is going to be the core of software engineering into the future. And I don't think your program is going to change. It's not going to go away, but it's going to be much more data centric and example centric than it ever has before.
Yeah, that's right. And in fact, if you think about it, right, machine learning today is much more powerful and can do much more automated things compared to what it could do 15 years ago. But I don't think anybody would say that, oh, now we need fewer people trained in machine learning, right? If
Yeah.
Europe, it's actually quite the opposite, right? Now everybody wants one. Because we see that there's now much more power in this technology.
So I noticed we've just got slipped slightly over time, so I apologize to your close, but I want to just first say thank you very much, Armando, for a very kind of provocative and grounded kind of talk about where we might be going with some of these things. So thank you all very much indeed, and I'll let you all go off to your next meetings. So thank you very much.
Thank you. Thanks a lot. Bye. Bye, everyone.
Thanks very much. Cheers.
Thank you.
Bye.
Thanks.